Hi there, and thanks for joining me for another episode of Draw, Make, and Code. I'm your host, Ed Cavett, and in this episode, I wanted to make some holiday snow. Here's an example of the output that we're going to generate in the program today. You can see it has a lot of dimension. The snowflakes that are in the background, or the small ones, are moving in proportion to their distance. The snowflakes in the foreground are falling faster, or appear to be falling faster, because they're closer to you. So there's a lot of illusions that you put together in this output, and collectively they generate this volume, this capricious movement, this kind of sleepy snowflake falling. And then the snowflakes themselves are not just dots, they're procedural snowflakes, and if you look real carefully you can see that they're changing in their geometry. I also wanted the system to be portable, so in a previous program I made some text art, and then I took the snowflakes and just moved that system into that code and zhushed it a little bit, stylized it so that I'd have an interesting title for this video. So this code that I'm going to create is going to be really easily portable into other programs. If you go to the p5.js website after you've donated, if you click on the examples page, it'll pull up the different sections. We want to look at the simulate section. You'll see there's a whole list of different systems. Many of those are particle systems, so you can see there are lots of different ways of approaching problems using particles, and that those systems can solve a lot of problems too. So the snowflakes example here, you can see from Adish Bhatia, the snowflakes are moving in kind of like a rotational movement. So they go to one side of the canvas and then they move back to the other side. And the particles are just dots. Now if we look down in the code, we can see that this is accomplished with a sinusoidal wave. That's how the particles are moving, and that they're kind of weighted so that larger particles are falling at a slightly different rate. So there is some thoughtfulness to the forces that are being applied to the particles in the system to generate some output that looks like snow. But you can see it's, I don't know, I feel like it's kind of mechanical. It could be glitter swirling in water at this point. So as far as snowflakes and snowfall goes, it's not very magical or holiday. It just suits the purpose of moving particles around. But if we wanted to stylize it and make it look more realistic in terms of the movement and the depth, and juxtapose that realism against the kind of cartoonish snowflake shapes, then it creates this interesting art, this kind of real looking cartoon place, this intersection. In order to accomplish the task of adding the realism, the scaled movements, the scaled size, the simplex noise to make sure that it's all in proportion, there's a lot of pieces. So to make it easier, I made a slide and broke up the different parts that we need to know about going into this challenge. Okay, so don't freak out at first. I know there's a lot of information on here, but let's go through it one section at a time. So the very first part, we want to give each particle a unique location. So we're just going to create a vector, give it a random width, set it to the top of the screen, or to start in a random place on the screen, and then we're just going to let it go. Since everything is factored to the scale of the snowflake, we want that distribution of size to be realistic as well. So we want there to be more small snowflakes in the background, we want there to be fewer large snowflakes in the foreground, and we do that with linear interpolation. I'll explain that here in a little while. Once we have the size of our particle, we can use that size quantity and then just subtract from the origin, draw a line from that point to the origin, and you have your lines to the left and the top. Add to the origin, you're going to get your lines to the right and the bottom. Once you have your horizontal and vertical line, then we want to make our snowflake shape with some cross lines, and those are going to be smaller. So we just take the size, multiply it times some coefficient, that's going to give us a smaller line, and then we use our diagonal coordinates to put that flake on there. And our forces, our color, our gravity, our wind, and friction, those are all scaled to size. So once we have the size of our snowflake and we've created its shape, we need to give it a color. that we can just map the size of the snowflake to a range of colors. So snowflakes in the foreground are brighter, snowflakes in the background are dimmer. Once you have their color, we can move on to gravity. Same thing here. Larger snowflakes have a faster fall. Smaller snowflakes will fall more slowly. And when you put that in the scene, it looks like there's perspective because that change in rate mixed with size, your brain is going to say they're all falling at the same rate. It's kind of a really cool illusion. Next we have the wind and the friction. Those are some multiple forces because there's lots of things that are happening, and I'll get into those in more detail later on, but that keeps them from falling straight down. They're going to be moving, swaying back and forth, left and right, and then as they're falling, I had this idea that to make the snowflake tumble so its geometry would change. That didn't quite work out, but I liked the changing geometry because it changes the shape of the snowflake, so I just kept it in. So we're going to factor that to the size of the snowflake as well. So it's going to be moving based on its size, it's going to be colored based on its size, and it's going to change its shape based on its size. So that's all the information that we need in order to get the system going into something that looks like this. Okay, now that we've got all of the details out of the way, let's start coding. So here's the code. I have it annotated in the version that's available in the link in the description, or you can find a copy of this on my GitHub. Also, if you're not a subscriber, I'd be honored if you'd support the channel by becoming a subscriber. Hit the bell icon to be notified whenever a new video is released. Hit the like, leave a comment, feed the algorithm, and that's going to keep everything going. So let's code. Very first thing you do is in your p5.js editor, we're going to start with the new sketch. In the global space, we're going to declare a variable called snow that's going to hold our particle system object. Then in setup, we're going to use the available window width and window height, and we're going to instantiate a new instance of our particle system object. I keep this as simple as possible because if you want to take this code and put it into another program, all you have to do is move the global variable, move the instantiation, and then in draw, we just are going to execute the update method of that function. So it's pretty easy. And also we're going to clear the background. We want a refreshed frame each time so that it'll animate it. It's not going to leave lines, basically. So that's the beginning part. Real easy. Keep it as simple as possible. So when we need to port this, we're just going to move the global variable, move the instantiation, and then move the update method, and then the function, and everything should work. So the function itself has a number of parts. It has the main body, and inside that it has a method that does the animation and generates the output. It also has a method that checks the locations to make sure that they're on the canvas. I don't want to waste processing particles that we can't see. So when a particle goes out of range, let's put it back on the canvas somewhere. If it needs to be reset like a new particle, we're just going to set it up to the top, give it maybe some new forces or whatever, and then let it go. So that's pretty much it for the function. In the instantiation part, because we're dealing with a particle system, we're going to set a number of variables into arrays. Those are going to be the position. So we need a variable to hold the location of each snowflake. We need a rate of descent. How are they falling? So each particle has to have a unique value for that, velocity. We also need a variable that will hold the size of the particle, since everything is related to the size of the particle, how fast it's moving, what its color is, so on and so forth. We need a variable for that. Also, we need variables to hold the unique forces that are being applied to each particle, like the airflow, the general airflow of the volume together collectively. And then there's like a breeze factor that's affecting the particles locally. And then there's another factor in the code that's related to the aerodynamics of each snowflake, because they're kind of tumbling in theory. They're going to be moving left or right or whatever. So I wanted to capture that movement as well. Also, I'm using simplex noise, so each particle needs to have a unique offset so it gets a unique range of noise values. And then a local variable to hold how many particles I'm using in this system. And then because I'm using linear interpolation to get the size of my particles, I'm getting that return inside the loop. And I'm using the assigned variable inside the arguments of the lerp. So it's kind of recursive. I can't do that recursion with a blank array variable. So I need a local variable that will hold the return from this lerp in this recursive way. And then I can just feed that value into the size element of the array that's holding the size. Sounds kind of complicated, and it was a little bit to figure out. I'm like, I can't do this the way I normally would because I don't have a constant variable. I have an array, and this array variable is changing. It's a different variable each time through the loop. But I need the return to be factored into the variable of the loop. So I need a constant variable to hold it. So that's what size set does. We send into the offset array a random number so that each particle has a unique set of noise values. And for the position, I want to give it a random location for the width, a random location along the height. And then this is where we start figuring the size. So I take the size set variable, I plug that into the lerp parameter, targeted to an ideal size. In this case, it's 5 units. And I move by 0.1. And what happens is the distance between the first return and the second return is going to be really wide. And then as it gets closer to the target, you get shorter and shorter distances, so more and more particles. Well, you can just use those values as a size factor. And if I'm going in the array from this, the return is going to be a large value to a small value, so just inverse that. So when I take this dot size and assign the value into the array, I'm going to take that size set value and subtract it from 7. That's going to give me at least a size of 2 for my smallest particle, and then a size of 7 for my largest particle. And it's going to go in the array from element 0 to the end of the array is going to be the smallest particle. When you get to the array's end, you're going to be at the largest particle. Does that make sense how that's being distributed? If it doesn't, leave me a comment. But anyway, let's move on to the velocity. We're going to set the x vector to 0. So it's not moving laterally, it's only moving vertically. And then we're going to multiply that vertical movement times some scaling factor so that the movement will be adjusted by size. So smaller particles are moving smaller sizes, larger particles are moving larger distances. Next are the forces. So the flow, the airflow is going to be a simplex noise return, so we can just set that to 0. The breeze is going to be unique to each particle, so we're going to give it a random coefficient. And the particles would look weird if they didn't kind of tumble a little bit. So to accomplish that effect, let's just rotate them by simplex noise. So a Perlin noise factored to their scale. And that's pretty much it for the initial state of these particles. So in an update, we're going to loop through those particles again and start animating their movements and generating their output. So we're using the noise statement, so we need some offset in order to move through these values, and I don't want each particle to have the same offset or the same range of returns, so I want to offset this a little bit uniquely for each particle. So to handle that, we just go into that y offset array and adjust each unique particle's offset by a small increment. Next, we want to add to the position the velocity vector, and this is going to account for gravity, and that's going to actually change the value of the position. And then after that, we're going to get our unique movement for each particle as it falls, and this has to be scaled. So we're going to take multiples of the size of the particle, and that's going to be this modifier that's going to move the, I think it's the x value left or right so much. It's not going to change the position, but when we output it, we're going to add to the position this flow variable, and then that's going to give it this movement back and forth relative to its actual particle position. And that kind of anchors that movement to a location without changing the actual location, which is kind of handy because you can do that and not have to test for bounds. But I add a wind force that's going to move things off the screen, so I have to test for bounds anyway. So this was kind of redundant. I could take this out and have the same effect, just added in a different way. So when I created this program, I didn't have the wind force in there. I just had this wobbling back and forth. So when I added the wind force, it kind of doubled up what I was already doing. So if you see that and you're like, why are you adding multiple forces that are basically the same forces? It's because it's left over and I just left it in instead of taking it out. But anyway, you have this extra variable that you can make adjustments to the actual position without changing it. So that's kind of handy if you want to change this into a brush of some kind. Next, we want the particles to rotate because we don't want them to just be in a static position as they fall down. That's not going to look very interesting. So let's move the rotational angle by simplex noise. And the range will be -2π to 2π, and that gives us a nice range of motion inside the simplex noise because it kind of gets clustered. So we want almost a full rotation. We don't want it to be clustered in like a half a rotation. So that's why the range is so wide there. You can play around with the offset coefficient and the range to get different rates of rotation. So those two variables will operate together to perform that goal. Next, we have that kind of the redundant variable, but this one is going to be actually added to the this.pause, so it's going to change that value. The flow variable doesn't change the position, it just adds to it in the output. But this is going to change the actual position, so it's going to look weird, it's kind of redundant, but you have that extra difference in how the variables change the original variable. So that's what this is doing here, and because it has to be scaled to the size of the particle, I'm going to use a local variable, get the return from that interpolation, and then multiply it times whatever that unit value is, and that's going to give us our change in the movement of the particle. And I think this is the generalized movement that affects all of the particles. Once we have our new position, let's test it to make sure that we're still on the canvas. If we're not, let's move to the canvas and do whatever we need to do to that particle. To do that, we're going to execute a method in this function called this.bounds. We're going to pass into the parameters of it which index value we're on, so we know which particle to adjust if it's off the canvas. And I think here I'm using brackets, it should be parentheses, so I'll change that. Once we have a valid location, then we can do the output. So we're going to isolate our output inside push and pop, and we want some unique color for our particle based on its size. So the shade is going to be brighter in front and darker in the back. So we'll do that with with just regular interpolation. We'll use a map function and use the size as our parameter and set that to some color range. And then we'll use that as the white value or all three RGB values in stroke. And then our stroke weight is going to be the size, so thicker strokes for the closer particles, narrow strokes for the ones that are way in back. And that will, if it's a decimal, it'll be a stroke of 1 by default. I think that's how that works. Once we have our color and our stroke weight, let's do another push and pop for some reason. I'm not sure why. I think because I translate and I had ideas for something else outside of that I didn't want translated to. So I just put the push and pop there. It's usually something I do whenever I'm translating and rotating. I always encapsulate that because I don't want it to freak out anything else in the global settings. So that's why that's there. And then we're going to translate to the particle's position. Now that's our origin. If we draw lines from that origin, we're going to be using negatives for the left and up, positives for the right and down. And then we can just use our size for that. So negative size goes to the left, positive size goes to the right, and up and down respectively. So it makes it really easy to draw things from an origin because you're flipping variables from positive to negative instead of subtracting them from whatever actual position, with an origin of 0, 0 being up in the upper left top corner. So once we've got our translation and we've rotated by our simplex noise return. Next, I had this idea where I would have the particles tumble. I talked about this a little bit earlier, and this is the variable that's doing it. But instead of tumbling, it's actually just shrinking the size of the lines. So it's giving you a modifier for the size of that geometry, and then it's going to adjust it by a multiple of whatever the size of the particle is. So that's what's happening inside flip. And because that's going to get renewed each time through the loop, I can just use a local variable. I don't need a global variable for that. Same with scale, which is just going to be an easy variable for the size, so I don't have to type the bracket and the index number. And now we just draw our lines. So each flake has a horizontal line and a vertical line, and those go from one side of the origin to the other side of the origin, vertically and horizontally, of course. And then we have two more lines that do the diagonal process. So once you get those typed in and figured out, you might miss a minus or a plus here or there. So just make sure that you have those correct, or else your flake's going to look weird and it might be hard to figure out. So once all that's done, close all those containers with push and pop. And I think that's it for update. Next we have the bounds test, where we reset the particles if we need to. In the bounds function, the bounds method that we have in this function, I should have passed into the parameters I. I did in update. When I executed the method, I passed in I in the parameter, but I have nothing to accept it here. So put an I in the parameters of the function there, and now we can use that index value to see which particle we're on and then change that particle if we need to. So we're going to use a condition. We're going to look at the y coordinate and see if it's off the canvas, and if it is, let's reset it back to the top. So we're going to give it a y coordinate of 0 and a vector, a horizontal vector that's random. Next we want to, I'm not exactly sure why I do this. I think this is just a hangover from when everything wasn't scaled, but I don't think it's necessary to reset the velocity. I do it here for some reason. I just create a vector, send the size into the y coordinate, and then multiply that vector times 1.25, just like I did in the instantiation part, but I don't think this is necessary. But anyway, I'm not going to take it out just because everything's working with it in there, so if it's not broke, it might be redundant, but it's still working. Next we want to test the X position, because we're actually changing that position. There's a chance it could go off the canvas and continue to go off out into nowhere. So let's set it back to the other side. If it goes off the left, let's put it back to the right. If it goes off the right, let's put it back to the left. So that's what's happening here. So I think that's everything in this code, except for I need to fix these small errors that I'm sure are there, like the one I just pointed out. When it gets down to test the bounds, it's going to call an error like it can't read this variable, or this variable doesn't exist, because there's no index value for it. So it's getting an NaN when it's trying to access that index value. So that's going to cause an error. And I think there was a couple others that we'll get to here, but let's, I guess, press play on this. Get my console window ready for my error message that I know is going to happen. And there it is. So it looks like switch move is not defined. So it's using switch move, but when I've declared that, I must have misspelled it. And I did. Switch those variables around. And that's not all. Okay, now we have I is not defined. This is where it's using I in the method, but there's no I passed into the variable. You're not going to see this a lot of times in tutorials where people actually will go walk through fixing mistakes, and I think that's a really important part of coding, is being able to read the messages and figure out what you did without it taking all day. I've spent forever looking for an error when all the information I needed was right there in the console, if I could have just learned how to read that better. So learning how to trace these errors down and fix them quickly is going to be a valuable asset. It's going to reduce a lot of the frustration that you get from coding. So learn how to fix your errors, learn how to read the mistakes, and just try not to make them. Of course, we know that's impossible. You're going to make some mistakes, but learning how to fix those when you do is going to be really important. So I think I've got it working now. This is what you should have in your output if you followed along with me and made all the same mistakes and fixed those. So here at the end, let's just scroll through the code so anybody typing along will get a clear picture of all of the lines, and if their output doesn't look the same, then you have an opportunity to freeze and check it out and see where you've mistyped things, just like I did. I guess that's it for this video. Thank you so much for watching. If you have any questions or comments, you have any ideas for a future video, leave it in the comments. Hit the thumbs up, subscribe, hit the bell, do all that. And as always, until next time, take care.